Okay, hi everybody. So we are going to kind of combine two lessons in one. So we are going to go over section 3-5, which deals with vertical asymptotes in the context of limits. And then in class on Thursday, we're going to take a look at horizontal asymptotes in the context of limits. So we've already looked at both vertical and horizontal asymptotes whenever we went over graphing rational functions. It's just now in this lesson we're going to take a look at them in the context of limits. So let's start with the definition of a vertical asymptote. So the line x is equal to a is a vertical asymptote of the function y is equal to f of x if either the limit as x approaches a from the left of f of x is positive infinity or negative infinity, or the limit as x approaches a from the right of f of x is positive infinity or negative infinity. So we know, given what we did looking at vertical asymptotes when graphing rational functions, we know that if our graph has a vertical asymptote, it forces our graph to either go to infinity or negative infinity as we approach that vertical asymptote. Okay, so we're going to take a look at a couple of vertical asymptotes in the context of limits, where the directions here ask us to evaluate the limit. For number one, we have the limit as x approaches 0 from the left of the function 1 over x squared. Now, truth be told, we can work through this limit in two different ways. I actually think because this function is relatively simple to graph, we can take a look at the graph of this function 1 over x squared. We know graphically the function looks like this. So we know that graph is going to lie in quadrants 1 and 2, like so. And we know that as the x values approach 0 from the left-hand side, the y values get closer and closer to infinity. So because the limit as x approaches 0 from the left of that function is infinity, that tells us that we have a vertical asymptote at the line x is equal to 0. So as I mentioned before, like not only do I want us to be able to evaluate limits, but also tell us, hey, what does that limit tell us about the graph of our function? Okay, so I'm going to leave that graph there because we're going to go back and revisit it in just a second. But we know that when like graphing rational functions, a lot of times the graphs of rational functions are really complicated. So we don't want to have to resort to sketching graphs of rational functions in order to determine limits at vertical asymptotes. Okay, so what we're going to do now is talk about like how can we analytically or algebraically determine what these limits are without having to resort to a graph. And the way that we do that is going to be exactly the same way in which we've approached limits up to this point. So the first thing we always want to check is, can we use direct substitution and get a valid output? We know if we can use direct substitution to get a valid output, then we do so, and that tells us that our point is going to be on the graph. If we try using direct substitution and get something of the form 0 over 0, like we did in the previous section, we know we have the three techniques where we can factor the numerator and denominator, multiply the numerator and denominator by a conjugate, or simplify the numerator and denominator. We'll eventually be able to cancel common factors, which means that that function is not in lowest terms. And then we'll eventually be able to use direct substitution to evaluate that limit, telling us that our graph has a hole. Well, with vertical asymptotes, when we try to use direct substitution, we're going to get something of the form some number that is not 0 divided by 0. So in this particular case, when I try plugging 0 in the place of x, I get 1 divided by 0. Well, if you take what you know about rational functions, like you kind of have an idea of what this limit is going to be, like some of the possibilities that this limit can be before we even like evaluate our limit. Because we know that the value that we're taking the limit at, which is at 0, we know that that is a 0 of our denominator in lowest term. So we know our graph has to have a vertical asymptote at x is equal to 0. So we just have to figure out, hey, is this limit going to go to infinity? Is the limit going to go to negative infinity? Or is the limit not going to exist? And we'll take a look at like when limits don't exist whenever we have vertical asymptotes in just a second. Okay, so because we get a number that is not 0 divided by 0, we have to approach this limit slightly differently. So what we're going to do is we're going to pick a value. Because we're taking the limit as x approaches 0 from the left, I want to pick a value that is close to 0, but because we're doing a left-hand limit, I want to pick a value that's slightly smaller than 0. So I don't know, let's say we pick like negative 0.1. Okay, when I plug negative 0.1 into my function in the place of x, I just want to determine if the output is going to be positive or negative, because if the output is positive, the limit is going to go to infinity. If the output is negative, the limit is going to go to negative infinity. So when I plug negative 0.1 in the place of x, we get 1 divided by a positive number, and 1 divided by a positive number is positive, thereby making that limit equal infinity. And that is how we analytically or algebraically evaluate limits at vertical asymptotes. Okay, so if we take a look at the limit on the right, it's a little bit different because we are not given a one-sided limit at 0. So when we're asked to take the limit as x approaches 0, like we have to check to see, hey, does the limit as x approaches 0 from the left-hand side of the function, does it equal the limit as x approaches 0 from the right side of the function? And if we take a look at the graph that we graphed for 1 over x squared, we see that both the left and right hand limits go to infinity, which makes the limit as x approaches 0 of that function go to infinity. Could we evaluate these limits analytically? Absolutely. Okay, so we already did the left-hand limit earlier. Let's do the right-hand limit really quick. Okay, so the limit as x approaches 0 from the right. So when I use direct substitution for this, we get 1 divided by 0. That's not a valid output. The fact that it gives me a number that is not 0 divided by 0, it tells me that I am looking at a vertical asymptote. Okay, which means that that limit, that one-sided limit, is either going to go to infinity or negative infinity. So if I pick a number slightly bigger than 0, because we're doing a right-hand limit at 0, let's say I pick 0.1. When I plug 0.1 in the place of x, my numerator is positive. The denominator, 0.1 squared, is also going to be positive, and a positive divided by a positive gives me a positive output, so I know that that limit goes to infinity. And since both the left and right-hand limits at 0 are infinity, the limit as x approaches 0 of that function is infinity as well. Okay, so I want you guys to do the same thing with number 2. Okay, I want you to take the limit as x approaches 0 from the right of 1 over x, and then the limit as x approaches 0 of 1 over x. So go ahead and pause the video to do that, and then we'll take a look at those together. Okay, so for number 2, just like we did with number 1, if you want, because this is a really simple function for us to graph, like we can evaluate this limit graphically. So the function 1 over x lies in quadrants 1 and 3. The limit as x approaches 0 from the right, so as our x values get close to 0 from the right, that function goes to infinity. So that limit is infinity. And if I want to take the limit on the right, so the limit as x approaches 0 of 1 over x, that limit is going to not exist. And the reason being is that the limit as x approaches 0 from the left of 1 over x and the limit as x approaches 0 from the right of 1 over x both the left and right-hand limits are not the same. The left-hand limit at 0 is going to go to negative infinity. The right-hand limit at 0 goes to positive infinity. So because those two limits are not the same, that limit does not exist, which, like, if you think about what we know about rational functions, that should make sense, because when we have a vertical asymptote and the multiplicity of our 0 on bottom is even, our graph has to go in the same direction. So that's why the limit that we found up above here was positive infinity. The graph goes in the same direction as we approach that limit, approach the limit as x approaches 0 from both sides. And then for the function 1 over x, the multiplicity of the 0 on bottom is 1. It's odd. So the graph goes in opposite directions as we approach that vertical asymptote. Okay. To take the limit analytically, so when I do the limit analytically for the limit as x approaches 0 from the right of 1 over x, if I use direct substitution, again, we get 1 over 0, which is not a valid output. The fact that it's a number that's not 0 divided by 0 means we're looking at a vertical asymptote. So I'm going to pick a value slightly bigger than 0. Let's say I pick 0.1. When I plug that into my function, we get 1 divided by 0.1, which is a positive number divided by a positive number, which gives me a positive output. So that limit there goes to infinity. And that's why we found this limit here to be negative infinity, because if I try using direct substitution, again, we get 1 divided by 0, which is not a valid output. So if I pick a number slightly smaller than 0, let's say I pick negative 0.1, when I plug into this function here, we get 1 divided by negative 0.1, a positive number divided by a negative number gives me a negative output, thereby making this limit here negative infinity. Okay, so that is how we evaluate limits of vertical asymptotes analytically. Okay, I'm going to have you guys try numbers 3 and 4. So for 3, we have the limit as x approaches negative 3 from the right of x plus 4 over x squared plus 8x plus 15. And for number 4, we have the limit as x approaches negative 5 from the left of the same function. All right, so go ahead and pause the video to give those two examples a try, and then we'll go over them together. Okay, so if we try using direct substitution here, the numerator is going to be negative 3 plus 4, which is 1. The denominator is going to be negative 3 squared, which is 9, plus 8 times negative 3, which is minus 24, plus 15, which winds up simplifying to 1 over 0. Same thing for number 4. Let's do this simultaneously. So when I plug in negative 5, we get negative 5 plus 4, which is negative 1, over negative 5 squared, which is 25, plus 8 times negative 5, which is minus 40, plus 15. Again, that is negative 1 over 0. So it's not a valid output. The fact that we get negative 1 divided by 0 means that, and 1 divided by 0 respectively, means that we are looking at vertical asymptotes. So we just have to figure out if the limit goes to infinity, does it go to negative infinity, or does the limit not exist? Okay, so let's go ahead and work both of these out. So what I'm going to do to start with, because both functions are the same, I'm going to factor the numerator and denominator because it makes it easier to like plug values in to test. Okay, so for 3, we get the limit as x approaches negative 3 from the right. Numerator is x plus 4, denominator factors to x plus 3 times x plus 5. And I'm going to do the same thing for number 4 as well. So for 4, we have the limit as x approaches negative 5 from the left of x plus 4 over x plus 3 times x plus 5. Okay, so again, I know that for number 3, I get 1 over 0. For number 4, I get negative 1 over 0. So I know for sure I'm looking at a vertical asymptote. We know that both of these functions are in lowest terms, and we know that negative 3 and negative 5 both make our denominator 0. So for sure we have vertical asymptotes here. So let's figure out whether these limits go to infinity or negative infinity. So if I pick a number slightly larger than negative 3, let's say I pick negative 2.9. Okay, when I plug that into my numerator, negative 2.9 plus 4 makes the numerator positive. Negative 2.9 plus 3 makes the first factor on bottom positive. And negative 2.9 plus 5 makes the second factor on bottom positive. So we have a positive divided by a positive, which is a positive quotient. So this limit here is going to go to positive infinity. What does that limit tell me? It tells me we have a vertical asymptote at x is equal to negative 3. But again, we should know that already based on what we know about rational functions and their graphs. Okay, when I do the same thing for number 4, when I pick a value slightly smaller than negative 5, let's say I pick negative 5.1. When I plug negative 5.1 in the place of x, we get a negative value in our numerator. Negative 5.1 plus 4 is negative. Our first factor on bottom, negative 5.1 plus 3 is negative. Our next factor on bottom, negative 5.1 plus 5, is also negative. So we get a negative times a negative on bottom, which is positive, and a negative divided by a positive is negative. So this limit here winds up going to negative infinity, again, which confirms we have a vertical asymptote at x is equal to negative 5. Okay, last example you guys are going to try is number 5. So for number 5, you have the limit as x approaches 5 from the left of x minus 5 divided by x squared minus 3x minus 10. So pause the video to give that example a try, and then we'll talk about it together. Okay, so again, with this one, step number 1 is to use direct substitution. So if we try using direct substitution, we get 5 minus 5, which makes our numerator 0. On bottom, we get 5 squared, which is 25, minus 3 times 5, which is 15, minus 10, which makes our denominator 0 as well. So we get something of the form 0 over 0. So we have to treat this limit differently than the ones that we've worked on so far today. This is most similar to what we did in the previous lesson. So if when we use direct substitution, we get 0 over 0, we can either factor, multiply by conjugate, or simplify to evaluate the limit. And I think in this particular case, factoring is the best. Now, I tried to trip you up a little bit with this example by taking the one-sided limit, the left-hand limit at 5. But it really, we treat it the same as we did all the other problems in our previous lesson. So numerator factored completely is x minus 5. That denominator factored completely is x minus 5 times x plus 2. We can eliminate that factor of x minus 5. So this gives us the limit as x approaches 5 from the left of 1 over x plus 2. Once I eliminate the factor of x minus 5, that was the factor that made both the numerator and denominator 0. So I can use direct substitution now. This becomes 1 over 5 plus 2, which is 1 over 7. So the value of that limit is 1 over 7. What does that limit tell me about the graph of my function? It tells me that there's a hole at the point 5, 1 over 7. So again, not only do I want you to be able to evaluate these limits, but also be able to state like what these limits tell us about the graph of our function. Okay, so that is the lesson that I would have gone over in class had I been there yesterday. Sorry I didn't make it. My son was feeling sick, so You guys should now be up to date, and then we'll go over horizontal asymptotes in the context of limits in class on Thursday. All right, hope you guys have a great rest of your day. Take care.